Welcome to the second part of our webinar, Perfect Switch from Rfem 5 to Rfem 6. I hope you attend the webinar last week that I presented. Today, I won't be the presenter. Andreas Niemeyer will do the presentation. I will be the moderator and I will answer your questions together with Florian Hiddemann. Yeah, how you can ask questions. I showed it at least for the attendees who participate the first time. I switch off my webcam that you can see the full screen. Yeah, just click on that button with the question mark, enter your question here, press send, and we will receive your question and we will answer you. The other way is to watch the entire webinar and then email questions to info@dlubal.com. Okay, that's all from my side for the moment. I hand over to Andreas Niemeyer. Andreas, it's your turn.
Thank you. Then I take over with the topics Perfect Switch from Rfem 5 to Rfem 6 Part 2. Today I want to show you in my program the differences between Rfem 5, Rfem 6 and show you points what you can do in our new software generation but you can't do in our old software generation. For this I selected, let's say, 5 main points. No? Understand and interpret the building, efficient usage of couplings, substructures save time, simply grasp reality, and finally evaluate results in a targeted manner. I know this point sounds pompous, but I selected this because, let's say, in the word is some reality and I really selected the examples to show you why. And this is now the point where I jump into the live demo with the main point, understand and interpret a building. For this we open a new model. I call it U1, and let's say, because we speak about buildings, I select here the add-on building model. This option changes or transfers the program to a building software. It gives, or it changes the mind that the program thinks like a building, it interprets it like a building, and how this is working and how you can specify a building now, I want to show you. For this I start, let's say, because I'm lazy, I start with a geometry input. I read in here below guide objects a background layer. I can select here DXF layer. You see it now here in the preview. This layer gives me the coordinates and the sizes of the buildings mainly. And because I just see, okay, the DXF is rotated, I can change it here. So you define here the angle and the program is rotating it, for example. After confirmation, we have it now in our plane, similar like the grid points, and can start modeling. Now this is, let's say, at the moment no building or something. It's only the, let's say, the limits of it. And so we start now with the building model and specify the stories. Let's say we have a 2-story building. The first story have a height of 5 meters. The second have maybe a height of 3.2 meters. Yeah. My target is to use different sizes. Why, you will directly see. And further I specify, hey program, please consider the, let's say, floors as rigid diaphragm in the 3D structure, and additional the slabs or ceilings what we have from the first and second story should be supported on, let's say, hinged supports. Of course you can select something, no? And now I confirm, and no blinking and highlighting infos will appear. Only you will see in the middle such a let's say dimension what shows us the height of the stories, not more and not less. And now we can start modeling the building. For this I use, for example, the column command. Let's say we have here beams. We know the beam should be a concrete rectangle, so I go into my library, select here a square rectangle, maybe with a size of 300, and a concrete, let's say C30. Let's select it here, C30, and you see the program directly find us the suitable concrete to this keyword, and we confirm this. It's going gray, and now we can start modeling. Let's say the exotic stuff is now, the program asked me here with a small dialogue, oh, do you want to have this column in story 1 or 0 or in both? In my case now both, and now I pick it. Oh, I can't find the snap point, so it's like in a CAD program, you can activate it here. Yeah? And now let's go to the other places, and maybe if it's easier we can use a top view and jump around this zack. Of course you can also copy if it fits. We have no rules for this. It's still like a Rfem that you can do everything in every stage, but now have a look. If we change to let's say isometric view, maybe make this box here. You see you have the columns here, and with the right length 5 meters 3.2. The same for, let's say, the ceilings. We can take here maybe a polygon floor plate, and we specify here, for example, we have a thickness of C30 and a thickness of maybe 22 centimeters, and go. And now let's say we pick, for example, the corners of the building for us, and maybe we realize, oh, we need it only for the first one and not for the others, so we can, let's say, change it during picking, because the program will realize it. And now you see we have this ceiling inside also with the opening for the stairway. If you want to do the same for, let's say, for the top, we go open again the command and say now maybe the upper story, and we pick the points here. And maybe this corner point here, and right click. Now we have the upper story. And now we see, oh, we have also walls here. No problem. There is also a wall command where you can select maybe different thickness, maybe here with 24 millimeters or centimeters, but for concrete. And if you pick it, you can say for which stories. I say for all. And now we define the wall should run from here to here, and the same for here to here, and maybe the last one from here to here. Now, so easy it is to define a building with walls, ceilings, columns, and now it works like before. We can apply maybe supports. So for example here also nodal supports. Now maybe here that we can grab all at once. Now, so this it is, not more not less. And of course we can start calculation, And you see the program is dividing the calculation job of the load case 1 in 3 parts. Why? And this why you will see now in the results. You see, maybe if I scale everything up, you see here we have 3 types of results: walls, floors, and both together. And this is now the way of thinking like a building. Yeah, you have now, for example, here only floors. This means the program interprets the floors as separate substructure. It calculates the ceiling with separate supports and separately. So I get for these elements only bending moments, but no membrane forces, because I assume these slabs works rigid in plane, that maybe the main structure of structure is working, but this ceiling itself I calculate separately. And the support reactions from the floors I transfer to the walls, that I can calculate the core of the building. This means in this model we have 3 calculations: one for the first ceiling, second, and for the walls itself. So it's separated, and this ceiling is not hanging on the top, for example. Yeah. So now let's say extend this example, and I prepared something. So I close this and I open, let's say, a more exhausting example regarding it's called building model. Yeah. So here you will see the same building with more stories, so with different story heights, so with a bottom floor, with a ground floor, with some regular floors, and a roof floor. And you see also here, for example, the increasing normal axis gradient of columns, because I just visualizing the wall result. Also the columns belong to it, and here we have our slab or ceiling, where you see these are the, let's say, ceilings here with water deflection because snow, but it acts separately. And if you visualize maybe the normal axis force, you see they are not, the lower slab have no effect to the upper. For example, if we show us here a live load, you see the live load maybe from this ceiling is going down but have no effect upwards. So with this type of calculation you can control the flow of forces. Further, you see with these results, if we watch here, for example, again this self-weight result, you get it not only graphical, then you get also a table for it, for this result. You see here in static analysis we have not only way of thinking for members, surfaces, solids, and also for stories. The program gives you information about the mass per story. The program gives you the center of mass for every story and the center of rigidity for every story. So it calculates it in this separate task. Further, you get for every, let's say, wall in this story, if you specify it, also, let's say, forces. So how you can define a wall. Here you see in your building model we have not only stories and floor sets, then also walls and deep beams. In this case I defined 3 walls, let's say. They have then a section like a beam, and one wall is this, and this in front here. And if I define it as wall, the program interprets it like a beam. Yeah, and all these forces you get locked down here in this table for every load case. You see the increasing normal force in load case self weight for wall 1, wall 2, wall 3, you get, let's say, story actions. These story actions are interesting if you take a look, for example, on wind. So we have, for example, here a wind load case in this horizontal direction. The building model allows you to interpret also the building like a diagram, and gives you the separate components per story. So maybe the wind load on top story brings 20.4, the next 30.2, 30.2, because we have a similar high. So everything is locked down what happens over the high of a building, and this should help you to interpret the buildings like it is, if you can, let's say, simplify it like this concept. Yeah, if you have some, let's say, stories in between what needs the transfer of, or the reaction of deflection or the stiffness of the floor set itself, you can control it here by defining if it's rigid or not, or if it's semi-rigid. So all these options are available per floor set. Yeah? So this brings me to, let's say, to the next point. What means if you have more complex building what are not only like this story-wise building, ceiling, column, and so on, and then of course you have to take all calculation options and to consider stages in between. And stages, for stages we created a further add-on, but to explain you how this is working, I prepared a model. Yeah? I called it construction stages, and this should give you imagination what or which type of issues or challenges could happen by designing buildings. Yeah? Here I have let's say a simple building. You have columns restrained on bottom, you have a beam what is let's say supported hinged on the columns, and you have a roof from timber what is also supported hinged here. Yeah? And if you watch, let's say, the forces from self-weight, at first everything is looking nice. Yeah? You get here in columns the increasing normal axis diagram clear. Yeah? But what is a little bit unclear, why I get such big compression forces in the timber beams according self-weight, even if there is no load on it. Yeah, and this topic comes because if the beam is bending through, so this massive concrete beam, it pull down the roof and it acts like a truss, and the result is that this beam here, this truss beam here, have tension, and this, let's say, is a little bit unreal. And this is exactly the point where you say, I cannot model everything in 3D. I have to take care what is being first and what is being afterwards. And for this we implemented, let's say, stages. Of course, such an option exists also in the old generation, but it was really restricted only according third order large deformation analysis. Now it's opened, it's completely worked in the program and opened for all calculation theories. How it's working? So at first maybe we make a stage. Let's say column. In the column stage we have members and nodal supports. The members is clear, this 2. Supports also clear, this 2. Then we have a next stage. Let's say the girder. Here let's assign, it's really easy, it's like bricklaying. Yeah. The next is roof. So for example, I selected these 3 stages with these elements. You can visualize it also. If you say here column, maybe I hide this, what is not active, girder, roof. Now the program have to know which loads acting on it. Yeah, so let's say clear. I want to design, let's say, column stage, girder stage, roof stage, and I expect that in stage 1 columns only self-weight and wind is acting. In girder is, let's say, wind acting additional, and in roof is acting snow and wind. And what happens now? The program is creating load combination for every stage. So you have here a separate column for stage 1, stage 2. So in stage 1 we get only self-weight and wind. For stage 2 we get self-weight and wind. For stage 3 we get self-weight, wind and snow. No? Yeah, and so easy it is. So when I design now this design situation, the program is calculating this design situation for every stage, and it's clear it cannot calculate all at the same time because the stages itself are always the basis for the next. What means if I calculate here stage 1 only for the column, let's say with wind, and they are loaded, will be deflected. Then we place the beam on it, it will be loaded, and finally get also the deflection. And here you see also the, let's say, brick camber, and on this deformed state we define finally for construction stage 3 the roof. And you see now in this type of analysis we have no tension force on it. And this is what I want to show you. Rfem 6 gives you now the option to work like this. Yeah, you can really define how you assemble it on your building site. And in comparison to Rfem 5, you have now the choice to use it according geometrical linear analysis, second order or third order analysis. It's even also possible that you say the stages itself should be analyzed according third order. And the individual load situations on these stages should be calculated linear. It's also possible. Then the program is changing the basis of this. So, further, this was now to the example, think like a building and interpret it. If you or we together come now to the next point, and this means efficient usage of couplings, because we coupled here, let's say if we take a look, the stages, so construction stage with load, but there are more couplings possible, and Rfem 6 or the new generation is living from it. This means I close this example and open a new example. What means I want to take over reactions. For this I have let's say where is this ceiling about first floor, and the second model ceiling about ground floor. Ceiling where it is, ground floor. To use the space of monitor, let's say I remove the spreadsheet and or organize it in these two views. So we have here first floor, here we have ground floor. What is this difference? Let's say go through model. If we maybe take a top view, you see we have here line support, so we simulate here a wall. And we have a load case self weight, we have maybe without results, we have a load here, we have a load here, and we have a load here, and all will be combined. In this model, maybe from top view, we have no wall below, so this is one big room. And if you take a look on this load cases, we have self weight, we have maybe one load for this room and we have one load for this room. And now the question appears, if I calculate this structure here, I get, let's say, for every load case, support reactions. When I activate it, we get deflections and of course also reactions. And now we have to apply these reactions on this model here. For this, I have to think about how I want to bring in. And the bringing in is for me now, I have here two basic independent load cases and I copy it 3 times and say, okay, this is maybe 3 from top, 4 from top and 5 from top. If you wish, you can also sum it up. You will directly see what happens now. Yeah. What we should avoid is we have here these 3 load cases exactly because moment 1 is clear, 2nd is clear. Here this because I copy it, we don't need a load on it here. Delete and delete. Yeah, so they are empty, these last 3. And now you can use for taking over the wizard. We have here import support reaction. You can say, I want to import it from ceiling about 1st floor. It's in the project from Dlubal Center. You say, you can decide you want to import support forces as object loads or as free loads from all supported nodes and lines on what means these lines and nodes, and on surface 3 and 5 it means these surfaces. See, in comparison to Rfem 5 we can use nodes and lines without exotic connections. Further, you can define automatically transfer to load cases, which means load case 1, surface load should run into load case 1. The other 3 load cases should run into, maybe manually, into 4, 5, 6. So here you really can decide which load direction should be moved or transferred. You see now the program visualizes it with question mark, and if I calculate it, the program will suction the reactions from the upper model, so from this, and define it as load on this. Use connections efficiently. This is the point what I want to show you. You don't have to write something, then it's done automatically. And what is really nice now, you see now surface weight clear, it's a permanent weight, and also on this case where we have a wall on top but below not, you get also a load here as free load. The regular load cases are not used like defined in the table, and here we have the loads from the separate load case, from this room, and from this room. And this is, let's say, a really efficient usage. And what is also really a difference to the old generation, if you have now the situation, for example, in permanent state, we have maybe a load from roof. So for example, I use a standard load with 1 here and here, and we have also a horizontal effect maybe in X. Let's use here 1, okay, and let's use here -1, that we have some roof load effect. And you specify now in the blower model, in the wizard, hey, program, please use for the permanent state not only Z direction, then also X component, and confirm it. The program wants to delete result. Yes, we have to save, clear. And now when we recalculate, the program is using the data from the model above, also the horizontal stuff, So it calculates at first the first floor above, and then it using these results in the lower one. And you see now in load case 1 we have now also this horizontal effect in the forces. Yeah? So this could be quite efficient in your work, and if you say I want to freeze him something, no problem, go here to disconnect and disconnect dependent model, go, then the program gives you, let's say for this load case, stupid loads what have no connection to something. No? So efficient usage of couplings. Yeah, you can use update it, but you can also break the update. And now let's come to the next coupling. Completely different topic, but it's also coupled. For this I close all and open a new scheme. Let's say you have to design a user-defined cross-section from aluminum. Yeah? For this I open our cross-section modeler. I call it UU1, for example. Yeah? And you know, in comparison to our old generation, in the old stage we had shape thin and shape massive, 2 programs. Now we have only 1, and you can decide here massive, thin walled. Yeah. Let's start with massive one and create, let's say, user-defined section from aluminum what is extruded. For this I open it, specify the material, what means make here a new row and write here maybe from label 60, 61 and use such a T6 material. And now we can start modeling this section, and of course you can do so many things, but I use these grid points now. So we have maybe here a line with 60, 60, 20, 20, some section like this. Yeah. This is now a polyline. I can extrude it, so you have here functions to extrude it. So let's say we have a thickness of 3 millimeters, so we extrude it 1.5 in left and we extrude it 1.5 in right. The center line we can break, and this, let's say these 2 lines we can select and can break it into single lines. Now let's say the geometry is closed. I close here, and because this is manufactured manually, I have here some roundings. I really, let's say I want to show you these roundings because this is always in connection or in conflict with, let's say, thin walled sections would have a, let's say, a stripe geometry, and this stripe geometry is always the break between massive and thin walled. And now we reached with our developer state that you can simulate both. So now this is let's say first part where we say, okay, this line geometry is from aluminum, we fill it with a material and we calculate it and we get section values. Yeah, quite easy. Now we say this section could be used in Rfem, and but you can't design it because the aluminum codes wants to know the C to T stripes regarding buckling and shear. And for this, it's no problem. In our section, you can extend it. You can say, yes, this is a thin walled, and additionally also aluminum stuff should be considered for the stripes. And now let's say, let's insert these stripes. Yeah, we can say we have here stripes with a thickness of 3 millimeters from this aluminum, and we insert it, and you see they are really rectangular and have here overstand, but this is no problem because we use for this mixed calculation of massive and thin walled sections, let's say for the bending relevant part, we use this part, and for the, let's say, shear and buckling relevant parts, we use these stripes, and you see the program will move these stripes intelligent according to these roundings. Yeah. So now when you calculate this, you get also section values, no problem, but then you can use it also for design, and this is the digital connection you can use efficiently. So I store it, and now you jump into Rfem, and you can, let's say, open a, let's say, make a easy aluminum calculation, call it a U7, and check here aluminum design, and yeah, let's define a new member. Define here section, go to library, say I have a user defined section UU1, yeah, and insert it into your model. The program is efficient, takes directly the material what you defined, it's hard coded, and now you can pick this member into your space. You see you have this geometry directly in your structure. You can, for me at the moment now it's irrelevant, we can support it. Of course we can also load it, maybe let's apply 2 kilonewton per meter, and yeah, and now the concept of Rfem 6 is working. You only pick on calculate all, and the program is doing the rest. So it's meshing, and then it creating combinations, and is doing the aluminum design. And you see you get not only deflection, then you get also let's say here a deflection curve. Yeah, so this is pretty cool. But now I want to show you the next stage. If you realize you made maybe an error, or you have a change, so the cross section changes a little bit, double click the member, and you have here a R section button, and this means the program opens the R section live inside Rfem in a special mode, and here you can say, yeah, I have a new stripe here because I forgot it, and you add it. Okay, and or maybe I read you because not that destroyed again, section from here to here. Yeah, and now of course now I know what I made wrong. Not from concrete and from aluminum. Yeah, now the color fits. Yeah, exactly. The program is realizing the same material, is merging this stuff so far, but these corners I don't like, because this is a little bit unnice. So let's say I change my view and optimize it. So I say here I have a rounding of 1, the inner curve, yeah, and the outer curve is maybe 4, and you see directly how these stripes are changing, no? And now you see, okay, this surface now gets written because it still has these lines into, yeah, so we remove it and change it to this, and now everything is fine. This stuff could be deleted, this stuff could be deleted, and now it's ready. We can save and return, and the program is updating this section. Okay, and now we have this section in our program. Yeah, and I press calculate all, use connections efficient, and you can directly design it. Yeah, so we really invested a lot of work in this live change of sections. You can do it for all type of sections, not only R sections and also standard sections. What should help you. And now you see you get directly a design. I hide it. design course for the new section. So now this brings me to the next main point. What means substructures save time? Substructures. Yeah, how to introduce you here. So I close this stuff, yeah, and open a new model. In this new model I define maybe at first a name, UU8, whatever, and I define here the multi-layer model. Why? You will see. Yeah? So at first our task or image for imagination, you're a designer, you have to create a story from timber frameworks. Of course we can read in a DXF floor plan, but now let's make it pretty easy. So I say when we are on top view, we can say our building is maybe typical 12 meters long, 9 meter width. We describe it really easily with here a few lines. Let's say 4 meter. So this is only my idea of an easy floor plan. Yeah, not more, not less. And now we say yes, okay, this floor plan should be created with 3 meter high timber frame walls. How you can do this? In this case, we select lines, copy, say okay, please create maybe copied minus 3 meter in high, create between original line and new line new surfaces, and the new surface should be a standard surface with, let's say, now the multi-layer add-on is coming in with a type beam panel. Yeah, and here you can specify sheeting. For example, we have a sheeting from manufactured timber. Yeah, so I select here one and define this is maybe orthotropic for surfaces. Yes, and the thickness is maybe 15 millimeters. And the same I use for the another sheeting on the other side, also 15 millimeters. And for the framing members, so the members around, I specify maybe a new section, maybe here a section from timber, new material, maybe a C24. Yeah, and the sizes are maybe 6 centimeter to 200 to 20 centimeters, that I have some space for insulation. Yeah, and we can select this section for all framing members. And now we have to specify the connection of the framing members to the sheeting. So I use staples with 1.5 40 with a distance of 74.5 millimeters, and for the inner studs I use this same section with a spacing of 625 millimeters. It's the width of the panels, and here we use also staples with 1.5 40 75. From this the program calculates the spring, how it's connected. Yeah. So now we have defined the thickness, and if we copy the line one story above, we get brown surfaces. Looks really nice so far. And now let's say we can support it. Maybe this support not. And because I'm interested what happens, I press on calculator. And you see, program is meshing. It needs some time. You see, load case 1 is calculated, and you get nothing. Yeah, strange. Yeah, and now the idea of substructures. Of course, you get here support forces. But where does it say rest? Yes, these surfaces gives us no result. Why? Because behind these surfaces we have substructures. We have here, let's say, beams with surfaces, with springs. So there's a really complex model behind, and we defined it only via surface. Yeah, and you can calculate it. And if you watch the forces, these are the normal axis force in the member, how the increasing normal axis force. Of course, you have to take care more about loading, but you see, you get calculatable model with this substructure idea. Yeah, and you don't have to model it by hand. We only copied surfaces. And now one step more. Imagine you have to define windows, of course, because it's really dark without windows. So let's create a window in front here. Yeah, so let's say we have maybe here a window, and yes, and we have maybe here a window. What happens? At first, nothing. But if I define here a cascading distribution of how to say, create surface cells around opening, if I create here lines, the program is able to make a cascadic orientation or a selection of the surface parts. And if I do this, the program is able to consider also windows with the, let's say, beam above, below, and also take care about the right distance of the vertical members. So it can really be a time saver, and you only define a few surfaces with a specific thickness type. Yeah. So this is one story of substructures. The second story, what is also important for me, is the mentioning of the load transfer surface. And for this, I prepared a model, so I close it. And this was an infinite wish in Rfem 5 generation. Yeah. The people ask us in support always, hey, do you have an element what have no effect for statics or for structure calculation, but can transfer loads? And we gave tips and hints to modify stiffness matrix and so on. Now we have it. So if you have here a typical structure and you have to load it by snow, yeah, why not? Make a load case, of course, we need one, so call it snow. Give here type, but this is maybe not the feature. The feature is that you have here a surface, maybe by boundary lines, and you have a specific type load transfer. Now you don't have to define thickness, material, because it's not needed. Yeah, it have no structural effects. And now we can pick it. Can pick the boundary lines to be concentrated, of course. Yeah, and now we have the surface inside. You see it in rendering, and now of course you can apply here maybe projected snow load in C, standard size is 1, and apply it. And if we calculate it, we get, let's say, forces on the structure. All thought this surface have no effect. So pretty cool. We have no surface forces. Yeah. You can watch what happens inside. Yeah. You can say surfaces. You can say here maybe load from distribution, and you see the program is distributing the load on the surface as homogeneous constant load around. If you say it should act only in one direction, go into properties and say only maybe in Y. Clear. And if you say maybe which functions was here more, you see isotropic finite element analysis. And the question appears, what is this? It's a substructure. And this means if I calculate this, the program have here such a load model below, what means he take out this surface in a separate model, hinge loaded supported hinged, calculate and take the reactions as loads for this structure. And this gives you a real picture of load distribution, yeah, from these surfaces. And of course this is cool because this surface have no effect for calculation, so you can really rule how forces are flowing, and you can use it not only for plane, then also for, let's say, curved surfaces. So I want to give you an idea how this is working. So for example, we have here a curved roof. So the beam is running in right direction. This is maybe vice versa, so we orientation. Now we say this beam is connected to this line, and yep, so structure is changing. Oh, maybe first we copy, it's easier. Now we can say this beam is connected to this, apply, and this beam is connected to this, and apply, and this surface is not plane, then maybe quadrangle, and have this line included. And now we have a curved surface, and if we calculate snow load again for this curved structure, it makes no difference. The program is taking out this curved surface, calculate distribution around, and use the reactions as loads on this timber structure. Yeah, so it's only your game to, let's say it's more complex. Imagine you have to do this by hand. How you use it, but substructures save time if you have such cases. Yeah. So, and now I come to the next point. Simply grasp reality. Yeah. Let's say this is always our task when we calculate, how we can grasp the reality so close as possible, but so rough as possible. For this, we extended our new generation with a few tools. Maybe the most famous one are here. So I have here one. Where it is? This is it. I don't find it. Torsion. Member torsion, yes. Yeah. So here's a really easy structure. I think everybody from us at first say, yes, I calculated by hand. Yeah. Simple beam, I section, pinned, supported against torsion here, with a main load vertical, or is the smaller horizontal load. What happens if we calculate it? If we calculate it, we get, let's say, we get here a few forces. Let's say, of course, we get a deflection. So let's say we have a vertical deflection, 1.9 centimeter. We have a horizontal deflection. We have a bending moment. We have a bending moment in this direction, 4.5. Yeah, take a look. This end up, let's say, in a stress, maybe only that you have something in mind, in an elastic stress of 280 Newton per square millimeter. And what is also interesting, imagine we have now here a pin support, a fork support. We have a biaxial bending, and we expect, or I would expect, also torsion, but torsion is 0. Now my question, of course, we get bending moments seems to be real, deflection seems to be real, but the torsion is questionable. Why we have no torsion? yes, maybe we have to activate in static analysis a few more checks or options. So let's say calculate according third order. Third order large deformation analysis is always able to consider all effects. Could be. Let's try. Yeah, calculate. So you see, meshing, static analysis is running. It seems we have some effects, and you see also solver have some vibration oscillations in it. Let's take a closer look on results. And wow, we have now a rotation of 845 millirad. Seems to be pretty big. Yeah. Also, if you take a look, bending moment MY clear, but now we have 220 kilonewton meter in horizontal direction from 3 kilonewton meter. Sounds a little bit strange to me. Yeah. And even stress 1616 Newton per square millimeter. Wow. Yeah. So it seems to me like a bug. Yeah. But you always have to grasp reality. Is the program able to consider this effect here? Yeah. We have an open cross section with a biaxial bending, what should induce some torsion. And the challenge is the program knows only 6 degrees of freedom. Yeah, it have no warping stiffness in it, and without considering this warping stiffness you are not really able to model such stuff with members. So our team implemented for you in Rfem 6, and this is now really new and gives you much more options, the warping torsion degree, the 7th degree of freedom of warping into the main calculation. You can connect it to first, second, third order as you wish, in branched models or only in one member models. And if we calculate it now, you will see you get results what fits a little bit more. Now we have a stress of 527 elastic stress. We have let's say a torsion of 81 millirad, so much smaller. We have maybe a bending moment MY is the same as before, and horizontal 28, so much smaller. And we have also a warping deflection to the end of the supports, and we have a primary torsion and a secondary torsion plus a warping moment on the structure. And with considering of the warping plus primary and secondary torsion, we are able to suction all effects what happens, and we are able to calculate so close to the reality as possible. So, and this could be connected to first, second, third order analysis. So this is what I want to show you, and you are able now to do it. You can use 7 degree of freedom in a member structure connected to shells in Rfem. This is really new. Now I want to come to the next point regarding simply grasp reality. And here, let's say I open a new example, especially regarding connections. So I call it joints design, and my example is so easy as possible. I have 2 beams, 1 girder. You see only 1 load case, but this is not the interesting stuff. I have only 1 load case to have a quick calculation as possible. But what are the genes of this model? Yeah, we have beams, we have now here stresses. Let's take a look on Mises stress. Maybe what is about 32 Newton per square millimeter on the beams. You see also here 0 point, and here again the restrainment on the column. Yeah. So far, let's say everything clear. And what is also interesting, we have here in the mid 65, here 47. But we don't know how the force is transferred from this girder to the beam. And for this job, we have, let's say, created an exhausting add-on called steel joints. And if I use this, I'm able to say on these nodes here, nodes, I want to create a joint. I can select from a again nodes from template now. Make it different. Right click. Now it's working. I can, let's say I have a really big library from connections, what you can also create user-defined ones, but here it gives you a first idea. For example, here we select this example and say, please assign this connection to this frame joints. Of course, program is doing it. It thinks about why, because you have to adapt this template to the new section sizes. And now we confirm it and say, yeah, looks good. This looks a little bit strange, so I don't like it. I modify it. I grasp reality. Yeah. So I say I want to have here a cap plate on beam 1, and then I think it's more like I like it. And now we grasp reality, we can specify weld sizes, everything, but here we can also say we want to do ultimate limit design, but also stiffness analysis. And we say, hey, please make an interaction between main structure. Let's say calculate initial stiffness and generate hinges in the main global model. And with doing this, I have to say the program, okay, please do it for member 1 or 2. And I say, yeah, please for the my degree for member 2. And now we can start calculation. Calculate all. And of course, I know this takes a while, but in comparison to Rfem 5, you have now a lot of more options. You can define now the connection like it is. So, do we have a cap plate or a stiffener? Do we have different bolt distances? Do we have weld lines? Do we have on every element a weld line? Is it bolted? Is it welded? It's your game. You can decide it. Additionally, you can because this technology models behind a shell model with nonlinear material law and checks light in the end the strengths. This allows you to apply normal axis force, shear force in Y, in Z direction, torsion moment, My and MC bending moment. So you can apply all forces. It's independent. It's allowed. Yeah, and we use this with this concept. Further, you can analyze not only forces and also unit deflection. So we can calculate stiffnesses from it, and now new also to assign it to the global model. So this is gives you a lot of options what you can't do in the old program, but now you can do. So you can recalculate really close to the reality. You can grasp the reality. Of course, maybe on the other side of the medal you have to wait. Clear. You can accelerate it by deselecting uninteresting load cases or by calculating parallel on cloud computing, what we also offer, but you get a few options more. And now you see what happens. Yeah, we get in the joints design. So let's open tables, go to the joints design. You get a utilization. You get maybe the design check written directly here for all what are done. You get a stress and strain view of the connection for every element separately. You can say, show me plastic strain, show me equivalent meso stress. And finally, you get also here hinges on the end of the members. So you have here type for members hinges where the program is writing you the diagram, the reaction or answer diagram of the connection to the model from the stiffness analysis. And if you watch now the result, if you go here to static analysis, you see now before we had here 65, now we have 74, and here we have 38. So the, let's say, this part is increased and this is decreased. So you can grasp reality now, interactive. And this brings me now, let's say, to the last point of my part today. What means evaluate results in a targeted manner. Still a pompous title, of course, but I want to show you which work our developers did for you, that you have an easy game in checking models. And for this I prepared here a structure. Where is it? Something with diagram. It should be. I don't. Here, calculation diagram. And let's take a look at first a model that you see what we are doing. So this is a simple beam, with a transversal load. The beam is modeled from shells. Web is a thickness of 6.5 millimeters. Flange have a thickness of 10 millimeters. The ends are supported with line support, so it reacts restrained. And if you watch the results, you will see we have some stress on the supports as expected because it's restrained, and we have some stress here. Maybe from color level we have a higher stress level here than here, but this is connected to the load what we have here. Now let's say I want to give you a picture what we want to do. Let's say I want to try to find out the carry-in level of this beam, what means how much load we can apply. Let's calculate to the plastic resistance. For this I activate in the add-ons, let's say the nonlinear material behavior plus a structure stability. Why nonlinear materials? Because I have to learn the material steel to be not linear isotropic, then to be nonlinear elastic for surfaces. What means this? You can select here for different diagram types. I take the easiest one, let's say elastic, and then the nonlinear elastic diagram at first with standard Young's modulus and then with a Hardeling modulus, and we yield at 235 Newton per square millimeter in the Mises format. What happens if I confirm this setting? Of course, results will be deleted. I can calculate again. And get results. Let's say the same, because we changed nothing on load and it's still elastic. So now let's try to come into the nonlinear elastic part to get some yielding effect. For this I take this base load and activate here stability analysis, and I don't want to calculate now buckling or something like this, and I want to increase loading stepwise. For this I take the method, incremental method without eigenvalue, and define here some parameters. My starting load factor, maybe we increase it always by factor 1. Refinement should be done with 5 in the last step, and we want to have maybe 10 increments. And because it makes for me no sense to calculate deflections from here to moon, we say let's stop at 15 centimeter max. And now, because this could be a one process and gives me a load increasing factor, or is I want to look inside this calculation. So I save the results of all steps. And if we do this, let's say the program have 2 steps. One for static analysis for the 10 kilonewton, of course, and the another is the load increasing step. You see now how we increase load stepwise. Now we come into this yielding effect. Of course, we see only the diagram now, not more, not less, so we cannot decide what happens. But now later we have to look into this result, and because we store every result separately, we have the chance. Of course, such a function works also in Rfem 5, but now we created something around what makes for you this thing easier. Now slowly you see we have increasing gradient. We are here on 10 centimeters, so slowly these reactions is uninteresting for me. We come close to the 15, and you will see what happens if the 15 appears, so you have full control. Now he stops and try a second look if it works. So he try again to load it in the last increment. The load factor is already reached so far. You can watch it during calculation, and now I think he will learn it makes no sense and stops calculation. So this is connected to the stability add-on. Only a robota function in this case. But what is now the change? In this view, nothing. Of course, we have to change here incremental method. And now we get a really interesting picture. Red in the middle, red on the right and left side. Seems like a plastic bending moment. Plastic load distribution. The same here. What is also new? You have here such a scaling factor. You can say this is load factor 7.2, this is load factor 1, what we saw before. Maybe you can change directly here in between. Further, you have the same box of this factor here on this result part. You can watch all results. The result what we just seeing is the Mises stress, so we have let's say the stress 235 here in the limit what we defined for yielding. What I like more is the criteria, because then I'm independent from the defined limit stress, so I have maybe yielding is defined with factor 1. So if you want to analyze it over length of the model, how you can do it? In this case we have this result cuts. We can say please cut for example only this surface, okay, and of course we have to solve from the mid to the other side, no? And we should visualize this result in y direction. Now you get the diagram here inside. Of course you can hide this and you see it much more better, but what I like more is to select it and to jump into such a result window. And this is now modal programmed, what is new in comparison to Rfem 5, because you can work at the same time in Rfem itself if you have 2 monitors. And now let's say we want to see deflection, maybe here u, and we want to see here criteria and y, and you have again here also you get here this increment bar where you say okay, this is load increment 1, then 2, no problem, 3, slowly we come here to the limit 1. Now you see you have here yielding slowly, and now suddenly here it's reached, and in the middle it's starting, so you can analyze it quite easily. And additional, what is also new now, is that you get here some, maybe you know it from you know it by Rfem 5, that you can drove above these surfaces and can pick something. I pick now one in begin, and I can pick one in the middle. And but for me these points are quite random placed, so I don't like this. But now in Rfem 6 you have the option to say, hey, these result points are typed for surfaces. They're stored here in this list, where you can specify it, and you can say, okay, the first one is maybe placed 1 centimeter inside the beam and in the middle, and the second is maybe in the middle of the beam, 2.5 meter, 0 and 0. So now the nodes or result points have the right place. If you show the result, maybe also here from the incremental analysis, you see maybe here values on surfaces, that you get here now a value. So far it's clear. Yeah, you can have these values here, but behind this, why I mention it, is now something new, what was not possible in the old. You have here a result diagram viewer, where you can say, please document me, for example, in the incremental method for the load case 1, in horizontal axis the load factor, and in the vertical axis maybe the surface equivalent stress Mises, the max one for the maybe surface web surface, and here not for any nodes, and really new for result points, maybe for the first one. And you see now, okay, how the load is now in near support elastically increased, and then you have this yielding effect. And if you copy this diagram and you can change it to the second point, you get it also, let's say, for the second diagram where it happens really later. And now this was always a wish, can I overlay it like in an overhead projector? And now you can do it. You can make a new diagram with a type group. The program is realizing similar diagrams, and now you have both results in one scheme. You see now the first one, the blue one, and then at any stage the second is also yielding and quite fast. Yeah. And of course the accuracy of this diagram depends on your steps, but this gives you options to analyze it in a targeted manner. And this is what I wanted to show you. And this brings me now to the end, and I hope I could show you with this few examples the differences to the old generation and how much work our team did to fulfill all these wishes what happened in the past, beside all general stuff.
Thank you, Andreas, for your nice presentation. I hope you could see good features or good reasons for switching from Rfem 5 to Rfem 6. Just try it out with the trial version, or maybe you bought the version 6 already. A hint, I showed that hint also last week. You can book the Rfem 6 course. It's a course for beginners. Click on that links, please, at the bottom for more information and for the prices. And you can also scan the QR code for our free courses. Okay, that's also all from my side. I thank you for your attention. Thanks to Andreas Niemeyer again for the presentation. Thanks to Florian Hittemann for the support by answering the questions. I hope we meet each other in a future webinar. Have a nice day. Bye-bye.